Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, HALO Lunar G2 module arrives in U.S., warming Mars with nanotech in a universe without dark matter or dark energy. HALO module arrives in U.S., advancing lunar gateway construction. The journey to establish humanity's first lunar space station, known as Gateway, has achieved a significant milestone with the arrival of the Habitation and Logistics Outpost, HALO, module in the United States. Fabricated by Thales Alenia Space in Turin, Italy, HALO's primary structure was meticulously crafted to serve as a foundational component of the Gateway Station. Its recent transport to Gilbert, Arizona, marks a pivotal step in the module's development, as it prepares for final outfitting by Northrop Grumman, the primary contractor responsible for integrating essential systems and equipment. HALO is designed to function as the initial pressurized living quarters for astronauts aboard Gateway. Drawing inspiration from Northrop Grumman's Cygnus spacecraft, the module maintains a diameter of approximately 3 meters but extends its length by an additional meter, culminating in a total length of around 7 meters. This design includes radial docking ports to accommodate visiting spacecraft, thereby enhancing the module's capacity to support crewed missions. Upon completion of its outfitting in Arizona, HALO will be transported to NASA's Kennedy Space Center in Florida. There, it will undergo integration with the Power and Propulsion Element, PPE, another critical component of Gateway. Managed by NASA's Glenn Research Center and constructed by Maxar Space Systems, the PPE is designed to provide power, high-rate communications, and orbital transfer capabilities for the Lunar Space Station. The combined HALO and PPE modules are slated for launch aboard a SpaceX Falcon Heavy rocket, setting the stage for their deployment into lunar orbit ahead of the Artemis 4 mission. Once operational, HALO will serve multiple functions aboard Gateway. It will provide habitation facilities for astronauts, offering space to live and work during their missions. Additionally, HALO will act as the command and control center for the station, overseeing operations and ensuring the safety and efficiency of various activities. The module is equipped with docking ports to accommodate spacecraft such as NASA's Orion, logistics vehicles, and lunar landers. Furthermore, it is designed to handle data processing, energy storage, power distribution, thermal regulation, and communications, all vital for sustaining long-duration missions in lunar orbit. The integration of HALO into Gateway represents a cornerstone of NASA's Artemis program, which aims to advance scientific research and exploration on and around the Moon. This initiative is not only focused on lunar endeavors but also serves as a preparatory step for future human missions to Mars. By establishing a sustainable presence in lunar orbit, Gateway will provide invaluable experience and infrastructure, facilitating humanity's next giant leap into deep space exploration. Warming Mars with nanotech. The quest to explore and potentially colonize Mars has been a focal point of scientific endeavors for decades. Ambitious plans are underway to dispatch both robotic and crewed missions to the Red Planet, aiming to assess its habitability for future human settlers. Establishing a sustainable human presence on Mars necessitates access to essential resources such as building materials and water, alongside advanced manufacturing technologies and self-sustaining habitation systems equipped with bioregenerative life support mechanisms. In essence, future Martian settlers must recreate Earth's self-sustaining ecological systems to survive and thrive in the Martian environment. Beyond establishing isolated habitats, long-term aspirations involve transforming Mars into a more Earth-like environment through a process known as terraforming. This concept has been explored extensively over the past half-century, with numerous proposals aiming to modify the Martian climate and atmosphere to support human life. A recent interdisciplinary study has introduced an innovative approach to warming Mars' atmosphere, utilizing nanoscale aerosols composed of graphene and aluminum. The research team, led by Associate Professor Edwin S. Kite from the University of Chicago, a member of the Curiosity rover's science team, includes experts from ELIS Research, Northwestern University, the University of Central Florida, the MIT Haystack Observatory, the European Center for Medium-Range Weather Forecasts, and NASA's Jet Propulsion Laboratory. Their findings were presented at the 2025 Lunar and Planetary Science Conference. Terraforming Mars involves 3 interconnected steps: warming the atmosphere, thickening the atmosphere, and melting the polar ice caps and permafrost. By initiating atmospheric warming, the polar ice caps and permafrost would melt, releasing liquid water onto the surface and water vapor into the atmosphere. The substantial amounts of dry ice present in the polar regions would sublimate, adding carbon dioxide to the atmosphere and enhancing the greenhouse effect, leading to further warming. According to Robert Zubrin in The Case for Mars, this process could increase atmospheric pressure to approximately 300 millibars, about 30% of Earth's sea level atmospheric pressure, allowing humans to stand outside without pressure suits, though they would still require warm clothing and supplemental oxygen. Previous proposals to achieve the initial warming phase have included distributing low-albedo materials or plants over the polar caps to absorb more solar radiation, as suggested by Carl Sagan in 1973. Other strategies have involved introducing greenhouse gases such as chlorofluorocarbons, CFCs, ammonia, or methane into the Martian atmosphere to trap heat. Additionally, concepts have been proposed to augment atmospheric carbon dioxide levels by harvesting it locally or importing it from other planets, with Venus being a prime candidate. However, these methods would require significant resource commitments and technological advancements that are not currently available. The novel approach presented by Kite and his team focuses on the use of engineered aerosols to induce atmospheric warming. Their research indicates that Mars' atmospheric dynamics and radiative processes could be harnessed to facilitate this warming, potentially serving as the first step in the planet's terraforming process. By releasing nanoscale aerosols of graphene and aluminum into the Martian atmosphere, these particles could absorb and scatter solar radiation, effectively trapping heat and initiating a warming cycle. This method leverages Mars' existing atmospheric conditions to create a feedback loop that could progressively lead to a more hospitable environment for human habitation. A universe without dark matter or dark energy. Dr. Richard Liu, professor of physics at the University of Alabama in Huntsville, has introduced a groundbreaking alternative to the conventional cosmological models that rely on the concepts of dark matter and dark energy to explain the universe's behavior. In a recent paper published in the journal Classical and Quantum Gravity, he presents a theory in which the universe expands not as a result of a singular Big Bang followed by continuous acceleration due to invisible forces, but rather through a sequence of discrete, rapid events known as transient temporal singularities. These singularities, he proposes, are fundamental bursts of matter and energy that affect all of space at once but occur in such brief moments that they evade detection. This mechanism, according to Liu, could naturally account for both the observed large-scale structure of the cosmos and the apparent acceleration of cosmic expansion without invoking unknown forms of energy or mass. The core of this new model replaces the need for dark energy's repulsive force and dark matter's gravitational scaffolding with a series of momentary surges in energy density. Each of these singularities floods the universe uniformly with matter and energy before vanishing just as suddenly, avoiding any contradiction with the conservation of mass and energy. Unlike traditional exotic proposals that invoke concepts such as negative mass or negative energy density, which have yet to be observed or reconciled with established physics, Liu's model operates within known physical laws by attributing the driving force of cosmic expansion to these brief, widespread events. Their effects remain hidden from current observational tools because they happen too infrequently and too quickly to be directly measured. However, the cumulative result of their influence would be a universe that appears to expand in an accelerating fashion, much like what has been observed through supernova surveys and other cosmological data, without ever requiring the presence of mysterious substances. Liu draws an indirect comparison to earlier cosmological models such as Sir Fred Hoyle's steady-state universe, where matter is created continuously to explain expansion without a Big Bang. Unlike Hoyle's hypothesis, which conflicts with the principle of mass-energy conservation, Liu's transient singularities involve no ongoing or continuous creation. Instead, they manifest briefly and globally, offering a theoretical framework that does not violate conservation laws. These bursts also give rise to what is known as negative pressure, a form of energy density that exerts a repulsive gravitational force, similar to what dark energy is supposed to do. This negative pressure contributes to the accelerating expansion of space, and in the context of Liu's theory, arises naturally from the behavior of these temporal singularities without requiring the addition of artificial constants or entities. In his explanation, Liu also references the concept of negative pressure in other physical systems, such as magnetic fields, and notes that Einstein himself included similar ideas in his original formulation of the cosmological constant. In Liu's model, this negative pressure complements positive mass-energy density while staying within acceptable physical constraints, which ensures that the total energy remains positive from the perspective of any observer moving uniformly through space. This subtle balance eliminates the need for speculative elements like negative density, which have plagued alternative models seeking to bypass dark energy. The implications of this new approach extend to the origins and persistence of galactic structures. According to Liu, the short bursts of energy and matter that characterize these singularities not only fill the universe uniformly at the moment of their appearance but also sow the seeds for density fluctuations. These fluctuations grow over time into the bound cosmic structures observed today, such as galaxies and clusters. In contrast to the prevailing cosmological model, which relies on a single singularity event, the Big Bang, followed by a smooth, gradual evolution driven by dark components, Liu's theory introduces multiple such events, each playing a role in shaping the observable universe. The spaces in between these bursts are void of the energy and matter typically attributed to dark phenomena, further supporting his claim that dark matter and dark energy are not omnipresent but occur only in brief, undetectable episodes. Looking ahead, Liu suggests that confirmation of his model does not necessarily require the capabilities of space-based observatories like the James Webb Space Telescope. Instead, he proposes that large, ground-based telescopes could carry out deep-field observations divided by redshift intervals, offering a possible way to detect the model's predictions. By analyzing how the relationship between redshift and distance behaves across different epochs of cosmic history, effectively slicing the data according to time, it might be possible to identify sudden shifts or irregularities in the Hubble diagram. These anomalies, if found, could serve as direct evidence of the discrete steps in expansion predicted by his theory. This method of observational validation gives the model an accessible path forward and may help bridge the gap between theoretical innovation and empirical confirmation. Through this new lens, the very foundation of our understanding of the cosmos may be re-examined, not by searching harder for dark matter and dark energy, but by exploring the possibility that they were never needed to begin with.